Fujita, and he will speak on uniqueness of K-polystable Fano interaction.
Okay, I'd like to thank the organizers for inviting me to speak. It's great to be here. And I'd like to say that the results in this talk are all joint with Chenyang Xu. And if time allows, I might talk about additional results that are joint with other people as well. So let me give a little bit of motivation for this problem before jumping into the topic. So I realize there are some experts in the room on this. But the motivation comes from looking at moduli spaces for varieties. So for curves, let's say that the genus is greater than 2. This is very classical. So we have this moduli space that parameterizes genus G curves. And then if we want to compactify this moduli space, then we should add some singular curves, which are the stable ones. Then we can also look at higher dimension analogs of these moduli spaces. So what's commonly accepted as the right generalization of this by birational geometers is the KSBA moduli space. So I'm fixing some Hilbert function h. And then what this is it parameterizes stable varieties with Hilbert function h. And what this means, we look at projective varieties X such that these objects have mild singularities, so they're semi-log canonical. The canonical bundle is ample as a Q-line bundle. And they have Hilbert polynomial H. Okay, so now that we have this very nice picture over here, one remark I should say about this, I guess it's a theorem, and I'm not going to cite people because there'd be too many people to cite, but it's an amazing result. But it's a theorem due to many birational geometers that I guess if you look at the corresponding, I guess I'm thinking about this as the coarse moduli space. Then this object is a projective scheme. So we have a very pretty picture at the end of the day. So now that we know these cases, what we want to look at is what is the correct moduli space to look at in the Fano case. So in the Fano case, there are a number of complications. So Fano varieties are very different from projectively polarized varieties in that they're not canonical models in the minimal model program. Some other complications is that they can have non-discrete automorphism group. But the one that I want to mention today is that there exists families of Fanos over the same curve. I'll call them X and X prime. So families of Fanos. And let's say that this is a pointed curve. So there exist families that are isomorphic away from the special point on the curve. But the special fibers are not isomorphic. So this means that if you try to construct a moduli space that parameterizes Fano varieties, your moduli space is not going to be separated, since each of these families corresponds to a... I'm being vague right now, but I'll be more specific a little bit later on. So let me just... yes, so this is my next statement. So I'll address that in a second. So the first thing, if you want an example of this, I guess there are a lot of examples that you can write down if you just look at KLT Fanos. And even in dimension 2, you can write down many examples, and some of the some particularly nice examples of this are due to Hacking and Prokhorov. And they look at degenerations of P2. So they show that there are many KLT Fano degenerations of P2, and one of them that you can write down, maybe the simplest one, is you can degenerate P2 to P114. So this gives a family whose special fiber is this, and the general fiber is P2. So if that's X and X prime is just the trivial family, you get one of these examples. So this is a singular example. If you want a smooth example, you can look at the work of Tien, where, let's hope I'm spelling this, Umemura. Thank you. So you can look at the Mukai Umemura threefolds, and Tien analyzed this in the setting of Kähler-Einstein metrics, and this will give you an example of something like this where all the fibers are smooth. Say that again? Or, so let me state one. Or, yeah, I wasn't sure.
There's a popular that has a triple T5, and there are two types of lines, and going up in line with the Fano, right? The one space is going to be something like the points.
Thank you. So one solution to this issue is that you shouldn't parameterize all Fano varieties, but you should parameterize K-polystable Fanos. So one thing to remark is that one reason why this is the correct moduli space to look at for Fano varieties is that K-stability and K-polystability, these notions are defined not just for Fano varieties, as Kento Fujita explained earlier, but they're actually defined for all polarized varieties. And one remark is that if we look at KSBA stable varieties, then these are all K-stable by the work of Odaka. So I guess our argument is that this is the right moduli, or these are the right objects to look at. So let me state one nice theorem related to this. So it's a theorem due to Li, Wang, and Xu, and also independently by Odaka. And what it says is that there exists a proper algebraic space parameterizing K-polystable smoothable Fanos of fixed dimension. So here when I say Fanos, I mean KLT Fanos. So it's expected that this is projective. Li, Wang, and Xu were able to show that an open set, or the open set that's parameterizing smooth ones, I think with discrete automorphism group, that is quasi-projective. And maybe, I guess Giulio will tell us a recent result about how you can extend that to a slightly larger open set as well. Okay. So now I want to say a few words about K-stability. So I know that Kento already gave us some definitions, but I want to think about things slightly differently. So I'll repeat a little bit of what he said, but hopefully not too much. So K-stability, as it was mentioned, is a notion due to Tien and Donaldson. And I guess in this talk, I'm not going to think about the version with test configurations, but I'll look at the kind of valuation viewpoint. So this was kind of first developed by Buxam, Hisamoto, and Johnson, and then we got these wonderful valuative, or this wonderful valuative criteria from Fujita and Chi Li and others. So from now on, X is going to be a KLT Fano, which means that X is projective, KLT, and minus KX is ample. And then I'm going to look at a divisor over X. So this is proper birational. Y is normal, and E is prime divisor. So as we saw previously, from the setup you can define some invariants. So the invariant that I'll look at is Fujita's beta invariant. And what this is it's essentially, in the notation of the previous talk, A minus S up to some scaling. So it's the log discrepancy times the volume. And then we subtract the integral of the volume function. Okay, so now, as we already saw, we can phrase K-stability in terms of this invariant over here. So this will be, I guess, the definition for the talk, but maybe I should really just call it a theorem, which is due to Fujita and Chi Li. So X is K semi-stable if and only if the beta invariant is non-negative for all E over X. And then X is K stable if and only if the same condition holds where you have strict inequality. Okay, so now I want to mention something. So there were 2 points of view in Kento's talk. So he talked about the definition of K-stability in terms of valuations, and he also mentioned the framework in terms of test configurations. So you can kind of go back and forth. So let me explain one direction. So if we have divisor over X, then this gives me a filtration of the section ring of my Fano variety. I'm going to be a little bit imprecise, but if if Kx is not Cartier but Q Cartier, then really I should be looking at the multiple over here. So the way this filtration is defined is that the pth part of this filtration corresponds to sections in the section ring, such that they take order of value at least p along our divisor e. So this means, I guess, I pull back s to y, and then I see how many times that section vanishes along e. OK, so now when we have this filtration, what we can do is look at the Riesz algebra of this filtration. So this gives us a way to degenerate the section ring over here to the associated graded ring of the filtration. So what this is the following object. So I add a variable t to just help me keep track of the grading by p. So this is a KT algebra. And we can look at this KT algebra, and if this is finally generated, over KT, then it's natural to write, consider the proj of this. OK, so now if you're familiar with basic properties of this Riesz construction, if you look at this proj away from 0, this is just isomorphic to the trivial family. And then the special fiber is the proj of the associated graded ring of the filtration. So one thing to note is that the special fiber over here has a GM action induced by this grading by P. So I should note that this construction over here actually gives us a test configuration. So this is a test configuration over A1. In Kento's talk, we looked at test configurations over P1, but you can just add the trivial fiber at infinity to get one, a compactification. So one other thing I should note is, in general, this Riesz algebra is not going to be finally generated. This corresponds to what Kento described as E being dreamy. But there's one nice condition when we know that this is actually finally generated. So if X is K semi-stable, so all beta are non-negative, and we have some divisor E such that the beta invariant is 0, then this is finally generated. So for a reference for this, you can look at my paper with Chen-Yang, but I guess the idea and really the proof of this is kind of coming from a paper of Li, Wang, and Xu. So that's where the idea is really in that paper. Okay, so now I'm going to define K-polystability similar to how Kento did, but you can define that X is K-polystable if one X is K-semistable, and the second part is that if you have some divisor such that the beta invariant equals 0, then I guess what Kento said was that E is a product type divisor, so it's induced by some GM. But for this talk, I want to phrase it slightly differently. So I'll say that then we can look at this degeneration induced by the divisor E, and we require that this is just isomorphic to the trivial family, or the trivial degeneration. So one thing that I should note about K-semistability and K-polystability, in general, K-semistable varieties can degenerate to different varieties or different K-semistable varieties. And I guess Li, Wang, and Xu showed that a K-semistable Fano degenerates to a uniquely determined K-polystable Fano. So this is related to the fact that we expect that K-polystable Fano varieties should be parameterized by some separated space. So now let me talk about the K-Moduli Conjecture, which essentially says that K-polystable Fano varieties have a nice moduli space. So what we look at is the stack that I'll denote K-semistable and then N comma V. And what this means is this is the stack parameterizing K-semistable Fanos of dimension n and volume v. So if you're, I guess, an expert on, I guess, the KSBA moduli space, what I really mean by this is that this is parameterizing families of Q Fanos, and I always assume that the family, or K-semistable Q Fanos, and I always assume that the family satisfies the Clark criterion and is Q Gorenstein. So the conjecture is that this is, first of all, an Arden stack. It's not going to be a DM stack because there are Fano varieties with non-discrete automorphism groups. And to prove a statement like this, one would first need to know that the set of Fano varieties over here is bounded, which is known by a result of Chen-Jiang that uses Burckhar's BAB. And then the second part of the conjecture is that there exists projective good moduli space so that corresponds to a map to an algebraic space, and I guess this algebraic space parameterizes K-polystable KLT Fanos of dimension n and volume v. So under this map, I guess two K-semi-stable Fanos should be mapped to the same point over here if they degenerate to the same K-polystable Fano. So I should note that I guess most of this conjecture is known for smoothable Fanos by the work of Li, Wang, and Xu, and also independent work of Odaka. So now let me talk about, I guess, the main theorem in this talk, which essentially verifies, which can be used to verify the separatedness of this moduli space if it existed. So the theorem, or the setup as the theorem, is, let's say, x and x prime. Let these be Q Gorenstein families of Q Fanos, and let's say that there exists some isomorphism or birational map which I'll call phi. That's an isomorphism over, I guess, C minus a point. So now from this setup, the natural question to ask is, are the two special fibers isomorphic, if we know that there's an isomorphism away from the special fibers? So the first statement is, if we know the special fibers are K-stable, then this birational map is actually an isomorphism over the entire curve. So in particular, these two special fibers are isomorphic. I'll get there, or I'll mention that in the next point. So all of my Q Fanos are, when I say Q Fano, I mean KLT Fano.
No boundary.
What?
No boundary.
So everything that I'll mention in this theorem works with a boundary, but to reduce notation, I'm not including it. So the next statement is, if the two special fibers are K-semi-stable, it's actually not true that this birational map extends to an isomorphism. We can see an example of that in a second. But what is true is that the two special fibers degenerate to a common K-semi-stable Fano. And the last statement really follows from the second one, is if the two special fibers are K-polystable, then the two special fibers are isomorphic. Any comments or questions?
Do you assume that it was single fiber? Are we
So I'm always assuming that the fibers of these maps are KLT Fanos.
all the fibers?
All fibers. But I guess you could always shrink. And I'm also assuming that the family is Q-Corenstein. So I'm assuming that the canonical divisor on X is Q Cartier and X prime. So one thing that I should remark about this theorem is that this was already proved by Li, Wang, and Xu, and similar type of result is in a paper of Spati, Sun, and Yao, when the generic fiber is smooth. And the proof they give uses the existence of a killer Einstein metric and analytic tools. Another thing, I guess, as I mentioned a second ago, or a minute ago, this statement works for log Fano pairs. There's actually, I guess, it requires some work to actually do steps 2 and 3, even though usually everything that works for Q Fanos works for pairs. Okay, so let me state one kind of easy corollary of this result. So a corollary is that if X is K-stable, so a K-stable KLT Fano, then the automorphism group of X is discrete. So I guess it's standard to deduce a statement like this from part 1. So since X is a Fano variety, we know that its automorphism group is a linear algebraic group, so it's affine. And I claim that the theorem, the first part of the theorem, implies that the automorphism group of X is proper. But since it's affine, it has to be discrete. So to see this in implication over here, note that if you have a map from a punctured curve to the automorphism group, this gives you a map from X cross C to X cross C. That's an isomorphism away from the special point. And then the theorem implies that this, I guess part 1 of the theorem implies that this map over here extends to an isomorphism over C, and then you actually get a family of automorphisms over C. Okay, so let me talk a little bit about the ideas that go into this statement over here. So maybe I'll erase this to keep the theorem on the board. So from this setup over here, let me just redraw what we have. So we have a birational map connecting X and X prime, and we have these two special fibers. So a natural thing to do is to take a proper birational model, y, that's dominating both x and x prime. And yeah, sorry.
So suppose there is a GM in the automorphism group.
Yeah.
How do you get it? Suppose there is the C star.
So I guess I guess the point is that the C star in the automorphism group extends to a whole A1 in the automorphism group.
It's just that in the automorphism group, you don't have the conclusion yet. And here you actually already have a family over A1. Yeah. But you start with just a family over C star.
Or so I have a family over C star or GM. So I have a map to the automorphism group. And then this gives me a birational map from x cross A1 to x cross A1 that's defined away from 0. Right? Where I guess the map is given by this is, I guess, if this is lambda, then I guess it's lambda t dot p comma t. So the theorem says that this birational map extends.
In the theorem, you already have conclusions. So in the first family, what is in the second family? In the non-trivial family, how do you need first to conclude somehow over 0?
Oh, sorry.
Yeah, you already have families over, not just over C minus 0, but over the entire C.
Or because, so the family over, so I just add the trivial fiber. Because I have the family x cross A1 and x cross A1.
You can do it even for the non-trivial family here.
Or I'm not sure, I'm not assuming that C is, or I guess this is local. I don't need C to be proper.
Maybe there is not. But I'll ask you.
All right, I'm happy to talk afterwards.
So this means what was true if your fibers are rationally rigid, right? So this is like generalization, right?
I guess,
It's a fiber weight. It's like a local.
Yeah, once fibers are rationally rigid. No. You cannot contract. Once contracted, it's all removed. Yeah. So this is generalization.
thank you. So the way we go about proving this is we look at this diagram, we take a model y that dominates both x and x prime, and then I can look at the strict transforms of the special fibers on y. Okay, so now what we first observe is that if I look at this special fiber or its strict transform on the right, then, one thing I should note is that we should assume that the two strict transforms are not the same. So if the two strict transforms are the same, you can show that this birational map over here actually extends to an isomorphism, because you can show that it's defined in away from. Oh yeah, sorry, if they're not the same. Thank you. Because then you can show that this map is defined away from a codimension 2 subset. And for simplicity, I'm just going to work in case 3. So I'm going to assume that the two special fibers are K-polystable. OK, so now what I do is I want to somehow use Fujita and Lee's valuative criterion. So we note that this divisor over here gives us a divisor over x. So that strict transform on the right actually induces a filtration, which I'll call F, of the section ring of the section ring on the left of the special fiber. So the way you get this filtration is that you say that a section is in the pth part of the filtration if and only if there exists some extension of S to the relative section ring. So I can always shrink C, so there's no problem with extending sections. What? Yeah, so the filtration is going to be on X naught. So I look at sections that extend to S tilde such that the order of vanishing on this strict transform is greater than or equal to P. So by extending sections, I get this filtration. And similarly, this strict transform on the left induces a filtration, which I'll call F prime of R prime, which is going to be the section ring of the special fiber on the right-hand side. Okay. So now I have these two different filtrations of the two different section rings. And the first observation we make is that there exists an isomorphism between the associated graded ring of the filtration on the left-hand side and the associated graded ring of the filtration on the right-hand side. And this isomorphism is a bit weird. So it sends the MP direct summand to a different direct summand, to the M comma M A plus A prime minus P summand, where A is the log discrepancy of this pair with respect to this exceptional divisor, and A prime is the other log discrepancy. So I'm not going to go through how you get this isomorphism, but essentially what you do is you take a section on the special fiber, you extend it, you pull it back to Y, but then you can compare the canonical bundle of the pullback of, you can compare the pullback of minus Kx with the pullback of minus Kx prime, and then you, I guess, push it forward and then restrict to the special fiber over here. Okay, so one thing to note about this is that what you can do is you can look at the Riesz algebra of the filtration as we did before, and you can take the corresponding prajas of these two objects, and these give you degenerations of the two special fibers over here, X naught and X naught prime, to the special fiber of the degeneration, which is going to be the praj of the associated graded rings. So what this isomorphism says is that the special fibers of these new degenerations are the same. So one thing to note about these degenerations is they're not really well-behaved objects right now because these Riesz algebras might not be finally generated. So the third step is to define the beta invariant of these filtrations. So you can do it kind of extending Fujita's beta invariant. So you have some log discrepancy times the volume, and then you subtract some integral of some volume function. But now we need to look at the volume of the filtration. So what you can write down is you can compute some limit and integrate this function over here. And you can define beta prime in the same exact way. So now the next step is to use this kind of isomorphism over here to relate these two beta invariants, and the isomorphism actually implies with a little bit of work that the beta invariants add up to 0. But now, since we know that our special fibers are K-semi-stable, you can actually show that these beta invariants have to be non-negative. So this means that these betas are equal to 0. So I didn't explain it, but the point is that you can try to compute the dimension of this vector space over here, and you can relate, I guess you can relate this integral to the dimensions of the associated graded rings and computing some limit in terms of the dimensions of these components over here. So then using this isomorphism over here, you can relate those dimensions. But I think it's not obvious if you just stare at the board. But
Before you were saying they're almost the same. Here you're saying they're
oh, yeah, so the reason why they're not the same.
You said the difference is 0. We would delete it easily, but you're saying the sum.
Yeah, so the reason why the sum is 0 is because this isn't quite, like, you're getting an isomorphism, but the isomorphism is switching the grading. So the pth part is going to the m times a plus a prime minus p part, and that's why these a, or like a and a prime show up in the beta invariant, or beta and beta prime, and that's why you're getting this sum going to 0. So.
Before you said that the fact that the Riesz algebra is finally generated is not always true,
Yeah, so we,
and then you get quantity semi-stable, x is semi-stable, and then dx of d is 0, then you have finite dimension. I don't think that it's easier.
So that's a very good point. So I'm about to get to that step in the proof. So give me 1 second and see if your question is answered. So the next step of the proof is, I guess, the most technical part of the proof, and it's to show that there exists a divisor E over the special fiber, such that this filtration that we constructed is actually f of E, and the beta we define over here is just beta of E. And similarly, there exists a divisor E prime over the other special fiber such that the same type of properties hold. Does this address your question?
Yeah.
So then,
I mean, this is the recursive though, because I think you are streaming already for
or so I guess the point is that
I
this,
think, maybe I'm misunderstanding, but I think you need to find a generation before you have the sum of this. here, since you use someone who's trying to create to work find integration back for the
Or like I agree with you at this point when I wrote down these prajas, like these are not finite type schemes. But like you can still write down this proj and you can still write down this isomorphism. But then at this step over here, once you get that there is some divisor E over X naught that induces this filtration, and that the beta over here agrees with beta of E, then you actually get that this filtration over here is finally generated. So let me just write down the last step. We're almost there, and then you can ask more questions. So at this point, we know that our filtrations are induced by divisors. But since X naught and X naught prime are K-polystable, and these degenerations over here are induced by divisors with beta equal to 0, this implies that this degeneration X is isomorphic to just the trivial degeneration. And now, since these degenerations are both the trivial degeneration with the same special fiber, this implies that the special fibers X naught and X naught prime that we started with are the same. So I guess this is, the end of the proof. So I'm happy to answer questions about this part before I move on. So I guess we had this diagram over here, and we wanted to say that if the two special fibers are K-polystable, then they're actually isomorphic to one another. So the idea was that...
But at the end, you conclude that they're just trivial.
Yeah, so at the end, so we start by constructing these degenerations over here. These filtrations might not be trivial, but we show that the degeneration...
At the end, you're saying if you have a degeneration and the central fiber is K-polystable, then it's product type.
Yeah, so I'm not saying that this is product type, but I'm saying that the degenerations tilde x and tilde x prime that we constructed using these filtrations are product type. But then, if we know that these are product type and they degenerate to the same guy, we started with the same Q Fano. Yes? So I'm always taking the proj with this respect to the M grading. I should have mentioned that. So P is indexed by, so P is indexed by Z, so P is actually giving you a GM action on all these guys. Yeah? Yeah. So I'm saying this is a technical part that there exist these divisors. So like, I'll say a few words about where it comes from. So that I guess we have this map from X to C, and we have this exceptional divisor, X naught prime tilde over it. So you want to extract that divisor over it. So we get some divisor, let's say F, and then, so we get some divisor F over X. And then you want to intersect F with the strict transform of X naught over here. And then you need to argue that that is actually a divisor and doesn't have multiple components. Okay, so let me, I know I only have 4 minutes, but let me just say a word about an application of this theorem over here. So we can look at the moduli of uniformly k-stable Fano varieties. So recall that uniform k-stability is a notion that was introduced in the work of Dervin and Buxom, Hisamoto, Johnson. And X KLT Fano is uniformly k-stable if and only if, I guess in Kento's notation, the discrepancy over S of E is strictly greater than 1. So this is stronger than k-stability. So I guess I should say this is a theorem. Okay, so now what one can do is instead of looking at the moduli of k-semi-stable Fanos, we can look at the moduli of uniformly k-stable Fano varieties. So it's a corollary of the main result I stated as well as other people's results, so I won't put a citation next to it. Or I won't. That if you look at this moduli stack, then this is a separated DM stack, and also admits it's coarsely represented by a separated algebraic space. So this follows from first a boundedness result by Jiang. So the set of uniformly k-stable Fano varieties of dimension n and volume v is bounded, and this uses Burkhar's BAB. The next part is so what this says is that all of these uniformly k-stable Fano varieties can be parameterized by some fixed Hilbert scheme, or the ones of dimension n and volume v. So then you might ask, is the set of those objects in the Hilbert scheme a constructible subset? We know that the set of KLT Fanos is constructible. So the next step you want is the openness of uniform k-stability. And this was proved recently with Yuchen Liu. So specifically, we say that in a family of or a Q-Gorenstein family of KLT Fanos, this function over here is lower semi-continuous. So we're able to get that the level set, or I guess the set where this value is greater than 1 is open. And then this means that I guess you get some constructible set inside the Hilbert scheme. And then you can quotient off by the choice of embedding. So you can quotient out by PGLN. So you get a quotient stack. And then to argue that it's a DM stack, you need that all the automorphism groups, or the stabilizers of the stack, are discrete. And that, of course, relates to the Mann theorem that I stated with Chen-Yang Xu. So now we know almost everything about this moduli space over here that we want to know. We expect that this is quasi-projective, and there's, I guess, some recent progress towards this in the work of Cadoni and Pathak-Falvey. But maybe I'll stop there. Thank you for listening.
Thank you very much. Were there more questions?
There's some philosophical questions. You can look at this folder where you have family, and you want basically to compactify in a different way. You remove center of fiber, and you think about different compactification. And in this case, normal bundle for the center of fiber is triggered.
Yeah.
For example, for negative normal bundle, it's without chilling.
Yeah.
About exceptionals, singularity basically. But what about like a positive ample normal bundle. For example, I tried to, yesterday was conference Korean-Russian topics, and one talk was about affine variants. Basically, the way automorphism of affine variants, and it's exactly the question was, if you have a sort of unique quantification of some sense, then it's very similar to this. Then the answer is all standard conditions. So it's basically the same question, but normal bundle is ample. So this is the first step from negative normal bundle, which was done by Chiang to the trivial one. You can think of it as uniqueness of invented quality. So can you like apply your message to the positive normal case? Like basically you have a fine variety, you add divisor of infinity. But suppose it's fun.
Yeah.
And in many cases you can do it
This way here.
No, it's
Fun.
not fun. Yes, there is fun kind, but imagine that you can simplify. So one typical question was, you have this P3 without cubic surface.
Yeah.
You add cubic surface. The cubic surface is a boundary, and it's if it's smooth one, it's fully stable. It's stable. So the question is, can you just simplify it in a different way, such that you have isomorphic cubic surface? It's Zaburin conjecture. Perfect answer is no, but in some sense it fits very well to this question. If you have such uniqueness in this case, then answer is this conjecture is impossible in one way.
I see, it seems like a very natural question, but I don't necessarily have a good answer.